Hello, good afternoon or good evening. Welcome to our session, Future of Energy with Connected Home. So in this session, we'll look at one of the largest utility energy provider in Europe, stepping into IoT space, building one of the largest connected home platform using AWS and AWS IoT services. And in the second part, we'll go a little bit deeper into AWS IoT services and actually looking at few architectural patterns for connected home. So without further ado, I would like to introduce Chris Livermore, head of connected home operations in Centrica. Chris.
Thank you, Claudio. So I'd like to start by talking very briefly about Centrica and Hive. So I work for Hive, which is part of the Centrica group. Centrica is a multinational company based in the United Kingdom. We own three major utility gas companies, British Gas in England, Bord Gáis in the Republic of Ireland, and Direct Energy in the US and Canada. They collectively have approximately 18 million customers between them. We also own the Dyno Group in the UK, which is a company providing domestic drainage and plumbing services. Local Heroes is the newest addition to our group, formed in 2016. And that provides on-demand access to local plumbing, heating, electrical and drainage experts. That's designed to meet the changing habits and needs of the next generation of Centrica customers who want a digital and pain-free solution when it comes to home services. And of course there's Hive, which I'm going to talk about a bit more in detail. But let me talk a little bit about British Gas first, because this is where it all started. British Gas can trace its origins back to 1812, when the Gaslight and Coke company started supplying gas for gas lighting. It was the first public utility company in the world. It ended up having to lay its own gas pipes to supply. It ended up having to maintain its own fleet of barges and ships. It owned railway locomotives and wagons, horse-drawn transport, and later cars and vans to support its energy company. And we take electric lighted for granted these days, but 200 years ago, this must have literally changed the way people led their lives. So fast forward to 1949, government legislation in England saw the public ownership, the private ownership publicised, and that formed British Gas. In 1997, 11 years after privatisation, British Gas demerged and the retail business was transferred to Centrica. And that brings us up to date with the Centrica group of companies. So British Gas also provides service and repair via its home care product, making it one of the largest UK providers of insurance products. And if any of you have ever had the pleasure of visiting London in the winter, you may have noticed at historic sites such as Buckingham Palace and the Houses of Parliament, some of the lighting has a warmer, slightly softer glow. We still have over 300 gas-powered lights in London, and they're still serviced by a dedicated team of British Gas engineers. So in 2012, British Gas formed a small sub-organisation, Connected Home, initially employing 15 people to create a remote control heating product, Hive. So British Gas had previously tested the connected home market with two products, Safe and Secure, which was an IoT security system, and RHC, a remote control heating product. And these had demonstrated that there was customer demand for these types of products. So Connected Home set up office in London, over 50 miles away from British Gas head office. We had few ties with our parent company and little or no access to British Gas infrastructure and technology. We were essentially starting from new. Connected Home's focus was on delivering a world-class remote heating product. We wanted to be innovative and disrupt the market, but at the same time, we were mindful of our heritage and reputation of our parent company. We needed to find a way to move fast, deliver on our promises while maintaining the values British Gas has worked so hard to establish. So as a new employee at Hive, I found myself caught up in an exciting whirlwind of startup energy, utilising new technologies, combined with the huge responsibility of maintaining the Centrica values and reputation. And actually, Hive is often referred to in marketing and publicity as a British gas innovation, which I think perfectly strikes the balance between allowing Hive to innovate and be slightly different, but also leveraging the values of quality and service that British Gas has built up and prides itself on. Our most widely recognised product is Hive Active Heating. Launched on October the 14th, 2013, it allows customers to remotely control their heating and hot water, set schedules via mobile or web app, and view both the inside and outside temperature at a property. Installations included with the purchase price of £249 and is carried out by a British Gas engineer, although you can home install if you want. The system consists of 3 components. We have a wireless thermostat, a boiler control module, and a hub. It's been designed to work standalone, so will continue to function and can be controlled locally in the event of internet connectivity problems. Hive Active Heating is available to any resident of the United Kingdom, regardless of energy supplier. In July 2015, we launched Hive version 2, featuring a brand new thermostat by renowned designer Yves Behar. The original thermostat had been criticised for being visually unattractive and difficult to program, much like every other thermostat on the market. Hive V2 not only looks radically different from the traditional thermostats, but it uses a more intuitive menu system, allowing most tasks to be achieved via prompted journeys and yes, no responses. The large rotary dial in the middle made temperature selection simple. Hive V2 also introduced 2 new features. Holiday mode allows the owner to set a separate schedule when they're away from home for a prolonged period of time, and boost mode allows a temporary boost to either the heating or hot water function. So along with the Hive V2 thermostat, we took the opportunity to upgrade the hub that was supplied as part of the package, which would allow us in future to deliver more devices and more features. In November 2015, we launched a multi-zone capacity, allowing customers to use different zones of their property to be controlled independently. In 2015, we also completed the acquisition of our technology partner, AlertMe, which I will talk about a little bit more in further slides. At the beginning of 2016, we added contact and motion sensors to the range of Hive products. We also added smart plugs. So smart plugs allow you to turn electrical devices on and off remotely, and contact and motion sensors do exactly what you'd expect them to do. We introduced recipes, which allow customers to create rules involving multiple devices. For example, to turn on a smart plug if motion is detected. And we announced a partnership with If This Then That, which allows integration with over 300 other devices and services. Following closed trials, we launched Boiler IQ in March 2016. So Boiler IQ is an IoT product that collects operational data from customers' gas boilers and uses that to determine the operational state of the appliance. Boiler IQ not only allows us to determine if the appliance is non-operational, but also in the majority of use cases to identify what the fault is and what the resolution is. This allows our engineers to arrive at the customer's property with the correct parts and equipment to rectify the problem. In certain scenarios, Boiler IQ can predictively identify failing components, and thus we can arrange repair before the unit fails. Boiler IQ is offered as an add-on to the British Gas home care product for £3 a month. You don't need to be a Hive customer to have Boiler IQ. The Boiler IQ clip-in can work with an existing Hive hub if you have one, but if a customer doesn't, we will supply one as part of the install. Approximately 55% of our Boiler IQ customers also have Hive. In 2016, we launched dimmable LEDs, closely followed by dimmable multicolour LED bulbs. We announced we would partner with Amazon's Alexa to allow voice control to activate lighting, plugs, and heating. We also launched our Hive camera. We launched a water flow and leak detector as part of an acquisition of a company called FlowGem we completed. We continue with plans to add more devices to the Hive family, as well as additional features to existing products, such as a recently launched Mimic Mode. Mimic Mode aims to fake occupancy when you're out by adding an element of randomness to on and off times of devices. And we also have a product called Heating Failure Alerts, where we can determine if your heating system is not working as designed by modeling the temperature changes in your property. So fast forward to 2017, Connected Homes has grown from 15 people in 2012 to one of the largest connected homes providers in the UK, currently employing over 600 people in 3 countries. In 2016, Centrica announced plans to invest 500 million into Connected Home by 2012, including a 65 million pound acquisition of our technology partner AlertMe. Connected Homes is now part of the Centrica Group alongside, rather than part of British Gas, reflecting both the importance of this sector to Centrica and our relationship with other parts of the Centrica family in addition to British Gas. So let's have a quick look at how Amazon Web Services has helped us to deliver the technology to support these products. So if we rewind the clock back to 2012 when Connected Homes was first created, how do 15 people in a remote office without the support and facilities of a large corporation go about delivering a product such as Hive? Our approach was to focus on the customer first and foremost. We identified the various touch points customers would have with our product and focused our effort on those. These were the mobile apps our customers would use to control their heating and our web presence, which would be both a shop window and a customer support portal. This was all built in Amazon Web Services. AWS became our compute platform of choice. Via its console and APIs, it gave our development teams control over the infrastructure, so they're able to move at their own pace without being dependent on network and systems engineers to build and configure their environments. Almost everything else, from communications and collaboration to our call centers and even our IoT platform itself, was provided by third-party suppliers. So earlier I said 200 years ago the Gaslight and Coke company had to build or invest in much of the support infrastructure it needed to support its primary business function. Today we have a multitude of companies offering their products as online services. Connected Homes chose to leverage services from industry leaders such as Amazon Web Services. Not only was this quicker to set up than building our own, it was low risk and we were able to choose service providers that were aligned with our goals and aspirations. Amazon IoT wasn't available in 2012. So we partnered with AlertMe, a UK-based IoT company with a proven track record, who British Gas had previously worked with on their safe and secure and RHC solutions, and who would provide us with both an IoT platform and our devices. So our first generation Hive platform wasn't in AWS. It was hosted on physical kit in a co-location facility in London, England. It was installed and managed by AlertMe, and as you'd expect, they chose a solution they had experience with, hence the physical hosted. The first 12 months of Hive proved some interesting technical challenges. So we'd chosen to use virtualization technology to run multiple workloads on a single physical server. So this proved invaluable later on, but it caused us a few teething problems as we determined the optimal configuration to run at scale. And it's only when you try and do things like this firsthand that you can appreciate the value of having someone like Amazon Web Services solve these problems for you. The initial success of Hive meant we outgrew the capacity of the hardware quicker than we anticipated. We'd not expected our customers to interact with a heating system as frequently as they did. Over 50% of our customers use Hive on a daily basis during the winter months. We had only a single rack available and no immediate expansion options. We were in the process of building a second installation at another location to provide us with multi-site resilience. However, this was both time-consuming and the technical challenge of ensuring consistency between both locations not inconsiderable. The staff who'd originally built the first site now found their time split between building the second site and general operational overheads of the first. In less than 12 months, we had to upgrade the memory, CPU, and disks within every single server in this installation. Because we'd virtualized, the task of upgrading was made easier, but it was still time-consuming and disruptive and expensive. Following the upgrade, there was then a real concern that whilst we'd successfully added more capacity to the system, we'd reached the maximum capacity the current installation could offer, and we had limited options available to add more capacity. And they were both time-consuming, expensive, and technically challenging. So we needed a system that could keep up with the growth of our customer base and our plans as a business. The solution was to migrate to AWS. So in September 2014, we launched our new platform in AWS. At a very high level, it looks something like this. So at the very simplest, we have our customers represented on the left-hand side of the diagram, and our hubs and devices represented on the right-hand side of the diagram. And in the center is all the infrastructure we need to support both the customers and the devices. The platform ran concurrently with our existing physical platform and allowed us to add new customers to the AWS platform whilst continuing to provide service to the customers of the old platform who would be migrated over time. Needless to say, this was all completely transparent to our customers. Architecturally, our AWS platform was very similar to our previously physically hosted platform. We mostly ran bespoke software packages on EC2 compute instances. We did, however, leverage AWS services for load balancing, ELBs, and one of our SQL data stores was hosted in a replicated Amazon RDS instance. Moving these to AWS reduced some of the operational overhead, mostly in terms of capacity management and disaster recovery. However, especially in the case of RDS, as we had an incumbent database team who were highly skilled at managing databases, it was not seen as a significant benefit. The most obvious benefit of moving to AWS was our ability to scale due to the elasticity of the cloud. But more fundamentally, it was the ability to scale on demand without limits. We could have scaled our colo facility. We could have purchased more rack space and more server capacity. And we could have bought more compute online gradually. But this would have been a slower, methodical approach. AWS lets us scale in reaction to real-time environments, real-time events, such as an extra load on our system due to time-sensitive promotions, changes in customer habits, or performance issues within the code that could be temporarily mitigated by additional compute. This ability to scale on demand ended many months of capacity planning, conversations, and meetings to reassure the stakeholders. The ability to scale doesn't simply apply to a single platform. We now had the ability to scale in terms of multiple platforms. We were able to run multiple dev instances concurrently without increased usage on one having an adverse effect on the others. We were able to run multiple concurrent platforms without having the overhead of having to maintain all of the infrastructure as a permanent asset. I spoke a few moments ago about our desire to build a second site and to provide fault tolerance. With the move to AWS, we gained the ability to spread our resources over 3 separate but interconnected sites within the same geographical region, and should we so desire, host in multiple regions. And this was no more complicated than a configuration option as we deployed our software. As with the scalability conversations, the ability to deploy to multiple availability zones reframed a number of long-running disaster recovery conversations. So today we run services in both the EU and US East regions. So our initial move to AWS was for the most part a lift and shift of our existing platform and technologies. As Hive continues to evolve and we continue to add new features and devices, we're leveraging Amazon services to provide us with a scalable, secure, reliable platform we can build on top of. And this really is, to my mind, a challenge of 2 halves. So on the left-hand side of the diagram, we have the parts of the system that allow our customers to interact with the devices on a daily basis. Despite this being an IoT product, our user-facing internet presence has a lot in common with many other high-volume websites. On the right-hand side of the diagram, we have our cloud-based services for managing IoT devices, receiving data and sending control messages, auditing, managing configuration and firmware. We also have the devices in people's homes and the remote management challenges they bring. So let's take a look at the left-hand side first. In many ways, this is a much easier problem to solve than the right-hand side. And when I say easy, things are only easy when you know what the answers are. But as I've said, the left-hand side is very akin to many other high-volume websites, and there's many patterns we can apply that have been used elsewhere. So if we draw that center line down our architecture diagram, we can clearly see what's on the left-hand side and what's on the right-hand side. I'm not quite sure at this moment where my device and temperature data live. Ideally, I'd want them on the left-hand side of the line, so they're easy to access for the customers. But they probably live on the right-hand side of the line because they're generated by the devices. So we'll worry about what to do with those in a bit. So starting on the far left, we have the public APIs and interfaces our web and mobile apps, and therefore our customers use to interact. As we add more devices and more customers, the load on these services increases. Hive is very fortunate to be in a continued growth phase at the moment. We add new customers on a daily basis, and we continue to develop new devices. Our previous platform consisted of a number of very tightly coupled services. A change to any one service on this diagram usually also required corresponding changes to all other services, and therefore releases were large and cumbersome. As we add more products, we need to introduce independence and ensure change to one product doesn't adversely affect customers using other products. API Gateway allows us to distribute our APIs over multiple back-end services. Put simply, this allows me to develop my user-facing systems as a number of discrete components and have API Gateway present them as a single interface. API Gateway also allows us to define our APIs on the gateway itself. This gives us added protection against remote exploits and denial of service attacks, as any invalid requests get fielded by Amazon and don't make it through to the infrastructure behind the API Gateway. So now I've got an API Gateway in front, I can choose to decouple my existing APIs, or in the case of adding new products, I can simply deliver them as a new standalone API alongside the existing ones. I can choose to deploy these as Amazon Lambdas. With Lambda, Amazon will execute and scale your code on demand without requiring you to run traditional EC2. Not only does this present scaling and cost efficiency opportunities, Amazon will scale as necessary based on demand and charge based on the number of requests, as opposed to EC2, which has fixed time-based costs regardless of usage. You'll also notice both API Gateway and Lambda are outside my availability zone. Amazon distribute these services over multiple availability zones in your chosen region without any extra effort on your part. So initially, we managed our user data, personal information, login credentials, etc., in an Amazon RDS instance, but we're now moving to AWS Cognito. So not only does Cognito scale on demand, and RDS does scale, but it requires manual intervention to do so, but Cognito also integrates with other AWS services such as DynamoDB and IoT that are also user-aware. So this allows us to build user-level security into our products if we so desire. So if you think about how a traditional database system works, the application code normally connects via a single username and password, and that can access all of the resources in the relevant data, in the relevant database. With Cognito, DynamoDB only allows access to the data on a per customer basis. So this drastically reduces the scope for application exploits, such as SQL injection or other external compromises, as the scope of any breach would be limited to only that authenticated user's data, rather than the contents of the entire database. We currently run our own Cassandra clusters for both temperature and device data. And we could store this data in a traditional relational database, but it lends itself more towards a NoSQL database, hence our choice of Cassandra. Our DBA team have done a fantastic job of building and running a large-scale Cassandra cluster in AWS, but it's not their core competency, and we've had a steep learning curve, and with many things, made a few mistakes along the way as we learn what works well for our use case. Unfortunately, sometimes the only way you can learn is from mistakes, and as a team and a business, we don't want to be using our production environment as a proving ground, but it's not always possible to replicate the scale and volume of data in dev test environments or mimic customer behaviors. For this reason, we're looking towards services such as DynamoDB. We can offload all the operational overhead to AWS, allowing my DBA team to refocus their efforts on the customers. We have confidence that DynamoDB is a mature, highly scalable service. I don't know for sure, but I suspect AWS have many customers using Dynamo for data volumes and rates far in excess of our use case. By buying into services like DynamoDB, we benefit from the combined knowledge and testing AWS have amassed from all their other customers and the improvements for the services these have driven. As an individual company, even one as large as Centrica, we couldn't hope to achieve even a fraction of that real-world experience with a large-scale data storage and replication that AWS demonstrates with DynamoDB. So if I superimpose our halfway line on the diagram now, you can see that not only does the left-hand side look much more simpler, but we can clearly see we're not running any traditional EC2 compute with all the traditional overheads of operating system maintenance and patching that entails. But we also no longer need to actively manage our data distribution over multiple AZs, as Amazon are taking care of this for us. So we've addressed most, if not all, of the technical challenges on the left-hand side. Let's have a closer look at the right-hand side. So what challenges are we facing on the right-hand side? Well, our first problem is probably speed. Certainly in the UK, home broadband speeds and coverage are variable. Having to query the devices in a customer's home every time they want to know the status adds significant latency. That latency doesn't provide a great experience from our customer, but it also presents capacity and scaling issues, as all of our cloud infrastructure is taking longer to respond to customer requests. It's essentially sitting there waiting for the requests to come back from the devices. So we're having to scale our cloud infrastructure larger than it should be to deal with these longer response times. So one solution to that could be to cache the device state in the cloud, and that presents challenges of its own. namely knowing when to trust your cache. With Hive devices such as our heating controls, smart plugs and bulbs, their state can be influenced in a number of ways, including physical interaction in the home, thus making it difficult to guarantee that any remote cache state is accurate. In the event of a difference between your cache and your device, which state takes precedence, and how do you deal with any discrepancies caused by the difference in state? Another major challenge we have is we cannot assume customers' devices will always be on. Light bulbs and plugs especially can be turned off at the main switch and disappear from the network for prolonged periods of time. Customers' broadband can also be offline. When hosting in AWS, we have many tools to ensure resources are always available. However, we have little control over some of the factors that can cause a customer's device to go offline. So how do we behave when a device is offline? If the customer simply wants to know some information such as the state of the device, we can probably fetch it from the cache, if one exists. But if the customer wants to control the device, then we have a different challenge. Are we able to cache the command and deliver it when the device comes back online? So that might be okay for some commands, such as renaming a device, but that might not be okay for other control commands. You wouldn't want to send a control to switch your heating or your light bulb on, only for it to be enacted hours, if not days later. The customer simply wouldn't understand the behavior that was going on. So we're rapidly approaching 1 million Hive installs, and every one of those devices is, in theory, always on and always sending data to our platform. This presents some interesting scaling challenges. So I previously worked in social gaming, where we would regularly have millions of people a day playing our games. However, not all at the same time. And those millions of people were distributed around the planet, and we had clear peaks and troughs of the load and the number of active players we had to deal with at any moment in time. With IoT devices, depending on the use case, you might find your entire customer base is always on and always connected to your platform, except when they're not. So we've already talked about devices not always being online. Operational evidence has shown us that we can lose large sets of customers due to planned or unplanned maintenance, for example, with ISPs. ISPs usually plan their maintenance windows to have as little effect as possible on their human users, i.e. at night. However, our devices are always on, and they're not humans. We've seen thousands of customers' homes go offline for significant periods of time. We've already discussed the challenges of dealing with offline devices. However, another challenge is how to deal with the thousands of devices coming back online at exactly the same moment when the problem is rectified. So most humans would retry a couple of times and then give up in frustration if their internet connection was down. Our early devices didn't behave this way. They kept trying and trying and trying to re-establish the connection until they were successful. When they were successful, we'd have many, many devices all trying to re-register with the platform at the same time, something it was not initially designed for. It was designed for a slow and constant addition of devices as we sold them. Additionally, whilst each device had been offline, it's still been collecting data. It's still been collecting temperature readings. And when it came back online, it tried to offload those to the platform as quickly as possible, causing us surge problems. So we have internal war stories from the early days of Hive, whereby the reconnection storm from an unrelated outage could cause us more problems than the outage itself. And those are just a few of the challenges that we need to solve on the right-hand side of this diagram. So AWS IoT solves a large number of these problems for us, and Claudio is going to talk about the technical details of that in a minute. Moving to AWS IoT has significantly reduced our development and administrative overhead. Not only do we benefit from AWS running and scaling this for us, but we also benefit from improvements AWS make from the service. So IoT is still an emerging technology, and we should expect to see many changes as the technology evolves, matures, and adopts standards. Amazon has a proven track record of delivering service improvements. By leveraging AWS IoT, we can benefit from these changes and ensure we remain compatible with new advances without the development and administrative overheads associated with running our own platform. So if you look at our architecture diagram now, you can see how we've managed to replace many of our bespoke components with a fully managed AWS services, freeing up development and operational resources to focus on delivering value to our customers. So I'm going to give you a few little insights into what we've learned from having these devices in our customers' homes. So probably the most important thing that we get from Hive is a Hive customer is a happy customer. We use a method called the Net Promoter Score. So we ask our customers, on a scale of 0 to 10, how likely would you be to recommend British Gas to a friend or colleague? And British Gas customers with Hive have an NPS more than 20 points higher than those without Hive. And when we ask Hive customers the question on a scale of 0 to 10, how likely would you be to recommend Hive to a friend or colleague, the score is higher still at over plus 40. Traditionally, it's been very easy to form a negative perception about utility companies. You only tend to interact with them when there's a problem, when you have to pay your bill, when your boiler's broken down. And media coverage, certainly in the UK, tends to focus on the negative aspects, such as price rises. Hive gives customers positive interactions that they then relate to their utility company. Being able to boost the heating before you get home early from work on a cold day, or giving you peace of mind that you've not left the iron on. These give our customers these little tiny positive interactions with us. We also know that people react to temperature differently. So historically, we've used weather forecasts to indicate when we can expect the big winter heating switch on. And it's been widely assumed this happens when the temperature drops below a certain degree. With Hive, we can see not only when people switch their heating on, we can see what temperature they've got their thermostat set to as part of their schedule. We know from usage data that people don't turn their heating on when the temperature drops below a certain magic temperature. They turn their heating on when they feel cold. And we know this is mostly influenced by the variance in temperature. So it's not when the temperature drops below a certain degree, but it's when the temperature differential on a day goes down by a large amount. So counterintuitively, this explains why we have customers in the colder northern parts of England who, as a generalization, set their temperature heating to lower than customers in the milder southern part of England. We also know that other influencing factors can include the visual aspects of the weather. So snowfall and snow on the ground tend to lead more people boosting their heating than they would do on exactly the same temperature on a day without snow. So this insight allows British Gas to better align resources with customer needs. We can use it to influence our supply chain, from parts through to engineer resourcing and call centre staffing. We can use it to provide a better out-of-the-box default setting for our products based on factors like time of year and location as we're doing the install. We also know that different properties have different thermal characteristics. Inadequate levels of insulation are often an issue in older buildings. With Hive, we can now accurately measure this. Again, we know both the internal and external temperature at the property. We know if your heating's on, and if it is on, we know what your target temperature is. So we can use this data to build a picture of the thermal behavior of your property. We can compare this behavior to other properties and thermal models to provide an efficiency rating. This can drive both our consumption forecasts and get valuable insight into the property owner on opportunities for improvement. Using this, we can also identify when the behavior of the property changes, perhaps due to a boiler or a heating fault, and we can alert the customer, and they can take proactive action. Finally, our Boiler IQ product provides us with some very specific insights and opportunities. So over 18% of Boiler IQ jobs are fixed first time specifically because of the replacement parts that Boiler IQ identified and that the engineer wouldn't otherwise have on their van. So for us and our customers, this means higher customer satisfaction because we can fix the job first time. We've also seen a 19% reduction in the need for engineer visits by using boiler data to give us and the customer the confidence to resolve issues over the phone. This gets customers up and running quicker, less disruption to their busy lives, as well as lowering overheads for us by avoiding expensive call-outs. The Net Promoter Score for British Gas customers who've had a new boiler install is 21 points higher if they have Boiler IQ. And this is a huge change in perception from what could otherwise be a brand-damaging experience for these customers having a boiler breakdown. Home care rates. The churn on home care customers drops by 2/3 for customers with Boiler IQ. a potentially huge benefit when you have well over 2 million home care customers with boiler cover. And now I'm going to hand over to Claudio to talk to some of the technical aspects about Amazon IoT. Thank you.
Thank you, Chris. I'm really excited to see all the developments and all the generations you guys worked in Connected Home. So now let's go a little bit inside AWS IoT and see how our services can help customers like Centrica developing and further optimize their connected home platforms. So when we talk about IoT at AWS, we really cluster the domain in three pillars. On one hand, we look at the devices, so all the sensors and actuators that are at the edge. Then we have the whole orchestration in the cloud with ingest and data processing and storage and visualization. And in the end, we have all the insights, all the intelligence we can derive out of the device data to create better and faster business decisions. So in the last couple of years, we developed several technologies for all these pillars. On the edge side, we have AWS Greengrass. Basically, it's our software for edge computing. You can install it on the local gateways to respond to local events, to operate offline, but also to simplify the device programming. You can start developing your algorithms with Lambda functions in the cloud and then deploy them on the edge using Greengrass. And of course, being able to run some of the business logic at the edge, you can filter some of the data. You can also decrease the cost of overall IoT applications. Moving on the second pillar, we have our core IoT platform, AWS IoT, and this is really our main service, cloud-based, for our customers to start developing IoT applications. You saw in Chris' presentation, AWS IoT icon there, replacing most of the custom developed. So let's go a little bit more inside AWS IoT and see which are the components that Centrica can use. So AWS IoT, it's quite a complex service, has all the key components that will allow our customers to provision a large number of devices, ingest data, but also start to apply business logic on the data streams. So first, we start with authentication and authorization of devices. When we designed AWS IoT, security came as a key design tenet. So we are using mutual authentication with certificates. We are using TLS 1.2 and X509 certificates. You also can define different policies for devices, fine-grained access controls, and of course you have all the tools for auditing and logging. Second, we have the concept of device shadow, which is a representation of the real device in the cloud. And the device shadow allows us to manage and persist the states of the devices. On one hand, being a virtual device, it has the last reported state, and from the applications or from the backend, you can set the desired state. So device shadow will always compare the two, and if there is a delta, will take the job to synchronize with the real device. One of the key components of AWS IoT platform is device gateway, which is actually our data broker to ingest at scale sensors data, device data. We support natively MQTT over WebSockets and also HTTP. You can set the quality of service 0 or 1 if you want to ensure the message delivery, and also support JSON formats. Once the devices are connected to AWS IoT, you have to tell what you want to do with the data. Do you want to store it? Do you want to perform additional algorithms? So for this, we have the rules engine, which is our service that allows you in a SQL format to filter the data, enrich the data, but also tell or where you want to dispatch it. You want to send it to a storage like S3 or DynamoDB. You can use additional Lambda functions to create complex event processing, but also you can use the artificial intelligence stack, so you can train with machine learning different models and then apply it to the ingested data. And finally, we have the device registry where you can store all the metadata of your devices. You can define device types, you can set up attributes, and basically create the first level for device management. So this is, let's say, a quick overview on the key components of AWS IoT. Now, for home automation architecture, in an abstract way, we can look at a very straightforward architecture. You have all the devices, the endpoints, the thermostat, the motion sensor, the light bulbs. They are locally connected, usually with a gateway, and then is fully managed with AWS IoT from the cloud. Now, this straightforward architecture, it's working well when you are dealing with a relatively small number of devices. But what happens when you have to go to 1 million or 2 million or 10 of million of devices? We did some prototypes with an appliance manufacturer that looked at 10 million endpoints, and their first calculation of messages per day reached 20 billion, which is quite a challenge. So we, together with Chris' team and Centrica, we tried to look into the architecture and identify some additional architectural patterns that will allow us to optimize the traffic and avoid a serious operational challenge of managing billions of messages every day. So these are few of the patterns we started to explore and prototype. And let's discuss a little bit on each of them. We have actually a session in the IoT track where we go in details at the architecture level with each of them. So the first one really refers to managing the states. Now, usually the devices will send every second or every few seconds what is the state of the device. Is the light on? Is the temperature 21 or any related state. Now, that creates a lot of traffic, and not all the information has to be real time. So on the first architectural pattern, we are looking to store the states of the devices at a gateway level, and instead of pushing them on every second or every few seconds, actually we design the application to pull only when it's needed. So if the customer wants to see what's the temperature in the house, it doesn't need to be sent every second, but just when he needed to read it. Second one is looking to the telemetry data, not the state, but really the all the readings like temperature or energy consumption. So again, instead of pushing it every second and create a lot of traffic, which might not be necessary, we can batch the telemetry data and send it to the cloud on a scheduled base, maybe every few hours or once a day or even once a week if the use case has a sense in this. Third, we can use with the AWS IoT a direct integration with the mobile apps. So that will allow a seamless integration and create a seamless experience from the user to manage the states of devices, but also get faster the telemetry for visualization. Of course, we have use cases when real-time data is required, but that can be activated on demand. It can be activated by the user in the configuration of an app, or maybe triggered by a certain event, so we can switch to real-time streaming. Another number 5, I think it's also very interesting, because we looked at the usage of home automation, and maybe more than half, maybe 70% of the actions are actually happening when the user is in the house, right? Turning on the light or changing the temperature. So building the mobile apps to be location aware and move to direct communication with the home gateway, again, creates a nice experience for the user. And in the end, with AWS IoT technology, with Lambda functions, we can train all the machine learning models in the cloud, but then the models can be pushed again at the edge and run, for example, in green grass, and create all the predictive, let's say, algorithms and decisions without being restricted to internet connection and having more flexibility. So overall, we took all these architectural patterns, and we really moved into a different architecture where we are balancing more the edge and the cloud, and create really a big impact in the number of messages that are streamed to the cloud, but also increasing the experience of the customers. So that's overall our progress and prototyping on the home automation. But yeah, we're going to use the rest of the time to open up for questions, if I can answer, or Chris. You want to come up? Thank you.